Let's suppose we have a furniture company that manufactures table and chairs. The table and chairs need to be worked on in two departments, assembly and finishing. The information about the labor hours required in each of these departments is given. We also know that each table earns the company $90 profit and each chair earns $25 profit. Assuming that the company will sell each item that it makes, how many tables and chairs should be made to maximize profit? Our first job is to write the linear programming problem, and therefore we need to choose some variables and determine what they represent. Often it's helpful to look at what the question is asking. How many tables and chairs? So we are going to let X and Y represent the numbers of tables and chairs. So we'll let X be the number of tables, and we'll let Y be the number of chairs. Sometimes it's helpful to make a table out of the given information. And I'm going to put tables and chairs across the top. Usually across the top, if I make a table, I'll put whatever my variables are going to represent, and then I'll put the other information down the side. Just makes it a little bit easier to write the constraints. We know about assembly for each of these, and we know about finishing for each of these. So assembly and finishing. We also know about profit for each of these. Okay. To complete a table requires 8 hours in assembly and 2 in finishing. A chair takes 2 in assembly and 1 in finishing. Now we have some total hours given for the assembly department and the finishing department. So I'm going to add a column here for total. It says that my total hours can be at most 400 in assembly and 120. Okay. And these are in one day, and so here both of these are per day also. Okay, let's figure out profit for each. Tables 90, chairs 25. From this, we're going to write our linear programming problem. First, we need to figure out, are we maximizing or minimizing? We are maximizing profit, so let's call it P. Now we need to figure out an equation for profit. We know that we make $90 for each table, so if we take 90 and we multiply it times the number of tables, that'll give us the total profit from tables. And then we're going to add to that the total profit from chairs, which will be 25 times the number of chairs. So 25Y. Now, we want to find our constraint. So we're going to have a constraint from assembling. We're going to have a constraint from finishing. Assembly. We know that the total hours has to be at most 400. So it can't go more than 400. Less than or equal to 400. Okay, how many hours do we spend assembling tables? 8 times the number of tables. Add to that 2 times the number of chairs. So 8x plus 2y is less than or equal to 400. Now we move to finishing. We know that we have 120 total labor hours or man hours here, so less than or equal to 120. We want to take 2 times the number of tables from here. So that's going to be 2x. That's the hours that we spend finishing tables, and we're going to add to that the number of hours we spend finishing chairs, so 1 times the number of chairs. Now we ask ourselves, does it make sense to have a negative number of tables or chairs? No, it doesn't. And so that tells us that x is greater than or equal to 0, y is greater than or equal to 0. Don't forget those non-negative constraints. Would it make sense to have 0 chairs or 0 tables? Sure, that would be fine. Maybe it'll be most profitable to make all tables and no chairs at all. It's certainly possible. We won't know until we get the problem done. So now what we want to do is we want to graph all these lines. So we look at this first one. We want to find the x and the y intercepts. We set x equal to 0. Let's go ahead and box this in so that we can find it. This is our mathematical model. If you're asked to write a mathematical model, make sure that you write whether you're going to maximize or minimize. Actually, this should say not maximizing, but it should say maximize, like that. It should say maximize. Have an equation there and an objective function, which you could label P or C or Z or whatever you like. Subject to, here's the constraints, and then my negative constraints will be listed at the end. So if we look at this first one, if we set our x equal to 0, so this part we cover up, and then my y will have to be 200. And then if I set my y equal to 0, so think of covering up the term that has y, so 400 divided by 8, which will be 50. Move to the next one. If I set my x equal to 0, then my y will be 120. If I set my y equal to 0, my x will be 60. So this is what I'll use to do my graphing. So on my x-axis, it looks like I can label them in 10. So 10, 20, 30, 40, 50, and 60. On my y's, we're going to do 20, 40, 60, 80, 100, and then here's 120. And then 140, 160, 180, and then here's 200. So the first line, we go through 0, 200, and then 50, 0. So we use our straight edge and draw our line. Don't forget to label it. So 8x plus 2y is equal to 400. Then we have 0, 120, 60, 0. So here's my second line. And I'm going to label that one also. So we have 2x plus y less than or equal to 120. We know we're in the first quadrant from our non-negative constraints. So now we do our shading. If we put in 0, 0 for our test point, that means the first one, let's write it down. Okay, so my first line will give me 0 less than or equal to 400, which is true, so that means I'm going to shade toward the origin like this. And now if I move to my second line, if I put in that 0, 0, I get 0 less than or equal to 120, which is also true. So once again, we shade toward the origin. And so now we look to see what area satisfies both of them. This area only satisfies one. This area out here doesn't satisfy either. This one only satisfies the second and not the first, but this area near the origin is going to satisfy both of them. So that's the one that I want. So we want all this in here. Sorry about that. Let's see if we can make that go away. Okay, I'm not sure why that went away, but we're going to fix it. Now they're back. Okay. So this is the area that we want. Okay, and let's mark our corner points. Here's one. Sure, we really are going up to the edge here. Here's another corner point, here's a corner point, here's a corner point. 3 of these we can get just by picking off our x and y intercepts. This one we need to find. So let's find this corner point. So I have 8x plus 2y equals 400, and I have 2x plus y equals 120. Let's multiply that second one by -2. And so now I have 2 -4x. And sorry, ran out of room. Let's try it. Let's just put them down here. Top one we'll leave the same. Second one we'll multiply by -2. That'll give me -4x, -2y, -240. Atoms, so that's this. So this gives me 4x. $160, so x is 40. And then if I put that into one of my equations, let's put it into 2x plus y equals 120. So 2 times 40 plus y equals 120. So y is equal to 120 minus 80, which is 40. So this point right here is 40, 40. So let's make my table with my corner points. I'm going to list out my corner points, and I'm also going to put my objective function for each of them. So for corner points, I have 40, 40. I have 0, 120. I have 0, 0, and I have 50, 0. So for each of these, I'm going to calculate that P. So 90 times 40 plus 25 times 40. Should give me 4,600. Here, 90 times 0 plus 120 times, sorry, scratch that. $25 times 120. That should give me 3,000. Here I'm going to get 0. Here I have 90 times 50 plus 25 times 0. So this one gives me 4,500. We want the max. Notice we have a bounded region, so we automatically have a maximum and a minimum. The smallest value will be the min. The largest value will be the max. So here is our max right here. And so that tells me that the company should make 40 chairs and 40 tables. Make sure you look up which one is which. In our case, since they happen to be the same, it doesn't matter, but that won't usually be the case. For a maximum profit of $4,600. That's our answer.